Okay, in this video podcast, I want to talk about the strengths of acids and bases. And I've talked here and there about strong acids and weak acids and strong bases and weak bases, but really haven't completely explained this concept. So I wanted to take this video podcast as an opportunity to do that. First of all, a strong acid or a strong base completely dissociates in aqueous solution. The operative word here is the word completely. All right, that means that when I place an acid or a base in water and it completely dissociates, in other words, completely breaks down into its component ions, I've got a strong acid or a strong base on my hands. So what are some examples? Well, let's start with the acids. The 6 most important strong acids that we need to know are as follows. The first one is one that we've used fairly extensively, and that's hydrochloric acid. When I place HCl or hydrochloric acid into water, what's going to happen is the hydrochloric acid is going to dissociate virtually completely. Now, it's probabilistic. Yes, it's true that there may be a HCl molecule here or there that it's not going to break down, but for our purposes, we're going to say 100% dissociation. Hydrochloric acid dissociates into H plus and Cl minus ions. We'll learn later that H plus is what drives the pH. So if we didn't know the hydrochloric acid concentration, we're going to know the hydrogen ion concentration because of the fact that hydrochloric acid will completely dissociate into hydrogen ions and chloride ions. The same thing is true of hydrobromic acid. Hydrobromic acid also a strong acid. It's going to break down completely into hydrogen ions and bromide ions. Hydroiodic acid, HI, also strong acid. H plus I minus. Perchloric acid, HClO4. HClO4, a strong acid. It breaks down completely into H plus and ClO4 minus ions. Nitric acid, a strong acid. HNO3 minus will completely break down into H plus and NO3 minus. And finally, sulfuric acid, H2SO4, breaks down completely. Let me just say just a couple of words about H2SO4, and that is H2SO4 is what we call a polyprotic acid, meaning that there are more than one hydrogens that come off. Obviously, the others have one hydrogen, H, but H2SO4 is an exception. H2SO4, we'll see it also with nitric acid, H3PO4, but H2SO4 has 2 hydrogens. Only the first hydrogen is considered easily removable. In other words, H2SO4 will dissociate into H plus and HSO4 minus, but once you've got the HSO4 minus, it's much more difficult to remove that hydrogen. So we consider H2SO4 to be a strong acid, but not HSO4 minus. There you have it. There they are. The 6 most important strong acids. You'll need to memorize those, so let's go over them again. Hydrochloric acid, hydrobromic acid, hydroiodic acid, perchloric acid, nitric acid, sulfuric acid. Those are the 6 strong acids. Well, what are the weak acids? Everything else. So once you've got these memorized, once you've got these 6 strong acids memorized, any other acid that we talk about is going to be a weak acid. But there are 2 in particular that I want you to remember. The first one is hydrofluoric acid, HF. That's a weak acid. It does not completely dissociate. We'll talk about that in just a minute. And acetic acid, CH3COOH. These are examples of weak acids. I want you to remember those specifically as examples of weak acids. Now, what does that mean? What does it mean to be a weak acid? Well, what it means is that they do not completely dissociate in water. We've talked about acetic acid. Acetic acid is CH3COOH. And when CH3COOH, by the way, that's vinegar, and when CH3COOH is placed into water, an equilibrium is formed. It's not an arrow solely to the right. That would be complete dissociation. This is an equilibrium. And so what happens is when I place that CH3COOH into water, I form 2 things. I form an acetate ion, that's CH3COO minus, and I form a hydrogen ion, H plus ion, okay? But the dissociation is not complete. There is a special number that we'll talk about. Because this is an equilibrium, there is a special number called a Ka, an equilibrium constant for acids. An equilibrium constant for acids, thus Ka, that we use to determine where along this equilibrium that most of the CH3COOH is and most of the CH3COO minus is. Just a quick note, a lot of people ask me, why do we write it as CH3COOH instead of CH4COOH? The reason is because of the fact that this is the hydrogen that we call acidic. In other words, when acetic acid is placed into water, these three hydrogens are absolutely stable. They're not going anywhere. It's this hydrogen which either will or will not be removed. That hydrogen right there, which will either leave or not leave to form acetate. And so we write it as CH3COOH, okay? So that's acetic acid. That's the equilibrium of acetic acid. It's an equilibrium. It's not a strong acid. It doesn't completely dissociate. Let's go to bases now. All alkali metal hydroxides are strong bases. What does that mean? Well, alkali metals, you recall from our study of the periodic table, are everything in the first column of the periodic table. So any hydroxides of alkali metals like lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and so on are going to be strong bases. Everything else is a weak base. Everything else is a weak base. Things that, by the way, hydroxides from the second column, things like beryllium hydroxide, magnesium hydroxide, tend not to be very soluble. They're not what we consider to be strong bases. But at any rate, everything in the first column then is a strong base. Along with that, I also want you to know that ammonia and the organic bases, sorry for the typo there, this is organic bases associated with it, such as ethylamine and dimethylamine, are considered weak bases. So there you have it. Strong acids, remember the 6, everything else, a weak acid. Strong bases, the alkali metal hydroxides are strong bases, ammonia, and the associated organic bases, ethylamine and dimethylamine, are considered weak bases. I'll see you on the next video podcast. Bye-bye.